Hi, Heiser. We might just have to do a one-on-one today. No, I'm just kidding. Everybody else is joining. Hi, guys. Can you give me a shout out if you can hear me okay?
We can hear you.
Okay, thanks, Carol. All right. Okay, guys. So let's get started here. And so we were talking about dynamic power consumption. And when we talk about that, this is in some ways it's fairly like an easy concept because you only have one equation to keep track of. And again, we've got the operating frequency of the circuit. Usually you're going to pick this to be your fastest clock frequency. And then this alpha is the activity factor. So that kind of divides down this operating frequency in some ways, given like how many circuits are active in a particular clock edge. So I think between alpha and F, you're basically considering how many circuits are switching. Okay, and then after that, you've got the total capacitance you're driving, and then the supply squared. Okay, so okay, so when you, like we said, power consumption is a very important characteristics, and we want to simply minimize it. There's never a situation where we don't want to minimize the power consumption. So what are the options? Well, we're really dependent on the power supply with the square law. Like I mentioned, if we have in our 1.8 volt process, which we've been doing our projects on, VDD is 1.8 volts. This is a 180 nanometer process. And, here 1.8 volts squared is 3.6 volts squared. And then if we were going to use a 90 nanometer or 65, let's just say 65 nanometer process. I think 90 still depends. So 65 nanometer process, VDD ends up being 1 volt. And that's, 1 volt squared. And you can see there's like a huge factor here, 3.6x difference in power consumption. So you want to minimize the power supply, and typically means that we want to go into a tighter process. So that is probably the best way to reduce power consumption. But then there's also want to drop your ways to try to reduce your frequency, capacitance, and activity factor. So let's take a look at some of those things. So, we talked about, I think we talked about what the activity factor typically is. Depends on a lot of assumptions about what your circuits are doing. But typically, not knowing anything more, if you have just a bunch of logic, this is, a lot of people assume the activity factor is just 10%. That means only 10% of your circuits are switching at any particular time. Okay. Then we have a bunch of stuff on how to calculate activity factor. I'm not sure that's really useful. But anyway, I think you just want to have that activity factor as this way to, as we saw in the example last time, sometimes you have like a memory block and that has a lower activity factor, and you know how often you address the memory block because you know what your microprocessor, for example, is doing. So you can use that, or a lot of times you just use 10% for random logic. Okay, so that's one. The second, this is the second thing you can do, and this is the best thing you can do in my experience, which is clock gating, and you'll see this a lot in logic design. So the idea behind this is, you have a master clock. Let's say, if I say, we've got this chip with, different blocks. You have, I don't know, ALUs and memory access. Maybe you're driving some external display. Okay, maybe you're reading data from an external camera, so on and so forth. There are a bunch of different blocks. And you have a master clock inside. So this is the master clock. What you do is you basically put a clock gate, so-called, that turns the clock on only in circuits that are being used. For example, let's say we know our camera isn't on. We basically turn off this clock going to this interface, this mobile interface. And so, those circuits just don't get clocked. So it's as if they're not, that capacitance isn't connected to anything. In fact, it's not. So what you do is basically you have a clock enable that's sitting there. So this would be, let's just say you have through this whole thing here, and you have the master clock that gets ANDed with this enable. Okay, and that acts as the clock for all the registers, all the flip-flops, all the timing circuits in this block being gated. So each one of these blocks would have their own gating enable signal, and you can just turn them off depending on whether you need them or not. Now, the reason you have a latch here and you're synchronizing your enable signal with the clock is if this enable was completely asynchronous with clock, you could end up having like some sort of half clocks and stuff run through here and completely wreck the status of this block, and you sort of put it in an unknown state. So it's really important to put a latch here to synchronize your enable logic with your clock. So this clock gating is extremely, extremely, extremely useful, and you'll see it a lot in logic designs. But it can also be pretty dangerous because depending on how this gating functions work, you could end up making some mistakes. So it's very careful. Whenever you almost always are going to see clock gating, and you always have to be like extremely careful. Of all the logic problems I've seen in chips over the years, I would say like maybe 80% of them are clock gating related. It just seems like it's just constantly an issue that's easy to get easy to get wrong and hard to verify that you're doing it correctly. But it's a very, very powerful technique. So if you guys are going to get into digital design or anything like that, you'll hear a lot about clock gating. Okay. So, the capacitance itself, you can try to minimize, as we'll see. Um, um, we talked a little bit about it. Wires themselves have capacitance, so you could reduce you could connect the blocks together to minimize the wiring. You could minimize the logic. You could optimize the logic. You're just basically reducing devices. You're reducing routing to reduce capacitance. So that's an option. Although usually the benefits of something like this are a lot less than clock gating. It's just it's a lot of work to optimize your layout. I think you always want to optimize your layout while you're doing it, but after the fact, it ends up being pretty difficult to get big benefits. The other thing that people do in advanced circuits is they have different voltage supply domains. Okay, so there's like I mentioned, we talked about how fast circuits run. So if you look at an inverter as a representative of all the gates, that's pretty bad looking inverter. So it's driving, other gates, other inverters and NAND gates, etc. But in sum total is basically driving some kind of a load, a capacitive load that represents all the logic gates that it's driving. And we can think of this guy as the speed of this guy being the amount of current that it pumps out or discharges this capacitor. The more the current, the faster you're charging and discharging the capacitor. Okay. Now, as your supply voltage drops, so if you keep reducing this, now notice this is, let's call this VDDL. So it's like lower than your normal. The previous circuit is also running on a lower supply voltage than normal, meaning that this logic high, logic 1, ends up being VDD low. That means that VGS, the gate source voltage of this NMOS, ends up being low. Let's say VDDL is, for whatever reason, let's say call it 1.4 volts, and VDD normal is 1.8 volts. Okay, so this VGS ends up being 1.4 volts instead of 1.8 volts for this device. And this current, at least most of the time or part of the time when it's in saturation, it's square law dependent on this VGS, meaning that you're dropping this current, you're slowing down the circuit, but you're reducing your power consumption because the power consumption is just dependent on CV squared F. So power is CV squared F, and you're reducing the supply. But if the circuit doesn't have to run as fast, or it's like in a particularly slow block, some blocks just don't have to be that fast. Some blocks are just, handling slow serial communication. They're, controlling some accelerometer or something that doesn't really require fast operation. So you can run it at a lower supply and basically run your fast circuits. Let's say you have a memory, like a DDR memory interface block. You'll run that at the full supply voltage because that needs to be as fast as possible. Okay, so the important thing that's also like a very effective. It's not as effective as clock gating. I would say maybe this is the second most effective approach. Is this is this different supply domains, and it's not uncommon. If you guys have played with microprocessors or FPGAs or whatever, you'll see several supplies. You'll see like it's very common to see like 1.2 volts, 1.8 volts, 3.3 volts. Like you need to supply all of these different voltages to your chip. It's very, 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 very common. And these are all different domains running in your chip that the designers have chosen to run off of these different domains. Now, one thing to be, so just like the clock gating can be very powerful, but also very dangerous. This can also be very dangerous, this activity. So you have to really also be careful. I've seen a lot of chips, not a lot, thankfully, maybe 3 or 4 have problems because of this. And for the following reason, okay, let's say you are driving let's say you're driving let's say you have a VDD low and a VDD high. Okay, let's say VDD high for the sake of discussion is 1.8 volts. Let's say VDD low for the sake of discussion is 1.2 volts. It's not that uncommon. Okay, now sometimes you'll have, so let's say you'll want to, by the way, one thing you want to do is make sure those are like sort of well separated. You don't want to be like physically having these things like all in a jumble because they're hard to keep track of. But let's say you have a sort of a high-speed domain running on 1.8 volts and a low-speed domain running 1.2 volts. And let's say you've got a signal going from the high-speed domain, from the high volt, sorry, I should have, well, that doesn't matter. So you got a signal going from the high voltage domain driving something in the low voltage domain. So this is 1.8 volts. This VDD low is 1.2 volts. Okay, so this is never, usually not problematic, because what happens, my my 1 voltage is going to be 1.8 volts. It's going to be, it'll be 1.8 volts here. It'll turn this guy on really hard, and the gate source of this PMOS ends up going negative. So it means you're just turning off this thing extra hard, but it'll still operate normally. Like you'll just turn this guy off and turn that guy on, and then your 0 is 0, and that just operates normally. You'll put the gate source across this PMOS. It'll be 1.2 volts. So about 0 here, 1.2 volts here. This guy will turn on, and you've turned this off. So that's okay, as long as you're going from high voltage to low voltage, you're okay. But if you just try to go, now do the reverse, if you want to go from a low, put that in green. If you want to go from a low voltage domain to a high voltage domain, you're driving that. Okay, so let's see what happens here. Your 0 is 0 volts, so that's okay. It'll turn this guy off. It'll put a VGS of 1.8 volt on this guy, turn it on. It's very good. The problem is with your 1. In this case, your 1 is 1.2 volts. okay, which is enough to turn this guy on. The VGS turns this guy on. But notice this guy. Its VGS isn't 0. It has a VGS of 0.6 volts. And depending on the threshold of this PMOS, it might mean that this PMOS is still going to be on when you have a 1 here. So you'll have an NMOS that's on and a PMOS that's also on. And you'll end up getting some indeterminate value here because this hasn't turned off when the input is a 1. So this is like a very, very bad situation to drive a signal from a low voltage to a high voltage domain. That can mean real problems. And I've seen circuits fail with that. So what you do in those interfaces, whenever you go from a low voltage domain to a high voltage domain, you build these specialty level shifter circuits. So level shifter circuits. And these things have these sort of positive feedback PMOS transistors connected on top. And what they do is, and then go to the high supply. So what these do is they translate the low signal level to the high signal level at their output. You have to be really careful with designing these, but once you have one of them, you can just sort of stamp them out all over the place. But you have to make sure you use these or you're going to have some serious problems. And the thing is, it's not always easy to see in simulation that you did this. Remember, you got a lot of circuits in your chip. It's easy to just do a quick simulation. In the simulation, you don't see anything funny and you go by it, but it turns up that your 1.2 volts is really ends up in real life being 1.1 volt because of the variation, and maybe your high voltage ends up being 1.9 volts, and all of a sudden you have a problem. Okay, so just be careful about that. Really good approach in terms of using different voltage domains, but you got to be careful, just like the clock gating. And then this is really for the advanced people. You see it a lot now in processors, etc., where you actually have something that's actively controlling the supply voltage. It's basically looking at the operating frequency. So let's say your circuit is running slowly, your voltage controller recognizes that, let's say it's in sleep mode or there's not a whole lot happening, and it actually reduces the supply voltage to the block actively. So basically on the fly. And then let's say the thing turns on because, I don't know, you started watching a video or something, and then all of a sudden it'll recognize that, that video processor block's doing a lot of stuff. So it'll raise the supply voltage to increase your speed. So that's also kind of a very nice approach. And you see it a lot. Okay, so that was all dynamic power. And again, dynamic power is all about this one equation, which is CV squared F. Okay, and we just talked about how you can try to reduce these parameters to reduce the dynamic power consumption. Okay, so this was for a long time, this was the only power consumption you had to worry about, because that was a nice thing about CMOS. If your circuits weren't switching, if they were just sitting there, they weren't taking up any power. But what happened along the line as the processes started shrinking in size, the leakage currents started going up, and now the static power starts being a significant effect. And the problem is, these transistors are sucking up power even when you're just sitting there. So here's an example. Okay, if you guys want to try to look at it. So we had this is going back to our previous example, right? We had, so nine, I think we had something like 9, let's see, what do we have? So we had 900, out of the 1 billion transistors in our previous example, we had 950 million transistors were memory. Okay, and this is saying that all these memories use a high threshold device. So if you guys remember, we had this the subthreshold current depended on, so if you just look at the subthreshold current, which was the biggest leakage current, I want to say it is I sub d. If you looked at it in the log sort of domain, this is linear VGS. What it looked like was when you hit VT, it didn't just go down to zero. Your current didn't go to zero. It would slowly sub threshold. So below sub threshold means below the threshold. Your current would drop, but wouldn't go to zero. And for every the subthreshold current, subthreshold current goes down by 10x for every 100 millivolts you're below V sub t. Okay, so and eventually it's going to be, you're going to be at zero, right? Because that's your input when your transistor's off is going to be, your VGS is going to be zero. So because you drop by a factor of 10 every 100 millivolts below V sub t, the higher this V sub t is, let's say your V sub t, let's say your high V sub t, so if high VT is 700 millivolts, then your subthreshold current by the time you hit zero is a factor of what, 10 to the 7th down, 10 to the 7th less than it was at V sub t. Now, if your V sub t was 300 millivolts, then the subthreshold current would have been 10 to the 3 down. So it's less. So basically you end up, lower threshold devices end up having a higher subthreshold current, leakage current going through them, just because of that, just because your V sub t is lower than the high threshold voltage if you keep everything else the same. Okay, the low V sub t devices are good because you know, it helps you switch faster because they'll have more current for the same VGS. You're going to end up having a higher drive current than you do with the high V sub t's, but then they'll have more leakage current. So it's this trade-off. So the high V sub t devices in our example, again, have a lower current, lower subthreshold current, 10 nanoamp, compared to the normal V sub t devices that are 100 nanoamps. So this tells me that the high V sub t devices, or the V sub t of high is 100 millivolts higher than normal V sub t, because there's a factor of 10 difference between the two leakage currents. Okay, so basically it's saying that we're using high V sub t for all the memories. So all these 950 million devices use high V sub t, and therefore they have 10 nanoamps per micron of gate length. Okay, and then 95% of the logic gates, so there were 50 million logic gates. So this is basically saying 95% of those logic gates don't have to be running very fast. So we used high V sub t for those as well. So times 0.95. So those are also at 10 nanoamps per micron. Okay. And then the rest of logic, so the other point, or the other 5% are at 100 nanoamps per micron. Okay, and then there's a gate leakage, which is, you know, the current, the leakage into the gate that we also have to consider. Now the gate leakage is the same for everything. It doesn't matter, you know, it doesn't depend on V sub t. So in this example, that's what we'll end up doing. And so what you'll see is, okay, so here the normal VT devices, they have a certain, so again, going back to the example from the last lecture, there was a certain, they had a certain average size. There was 50 million of them. They had a certain average size, and they made up basically they make up 5% of the logic gates. So total of this much width, because remember this is per width. So we want to figure out what the total width is for the normal VT devices. The high VT devices were the 95% of their 50 million, so the remaining, and sort of the same size, and 950 million memory devices, okay, which are smaller. And so they gave us this much total width. And basically we multiply the normal VT, the total normal VT size width times 100 nanoamps per micron, and the total width of the high VT by 10 nanoamps per micron, and we get this number, 584 milliamps, which is pretty big. And then the gate current, it doesn't matter, we're just summing up all the widths of the high and high VT, low VT, doesn't matter, they all have the same gate leakage current. Okay, and you end up having 275 milliamps. Now, I forgot to mention this. You see this gets divided by 2, and actually this also gets divided by 2, because we're assuming for something like this that, you know, half the devices are on, half the devices have a logic 1 on them, and the other half of the devices have a logic low or a 0 on them. Okay, so anyway, all in all, we end up with, we sum all these guys multiplied by the supply voltage, which was 1 volt in this case, so we get the total current multiplied. So this power, static power, is VDD times total I leakage. Okay, so this is the I leakage, this is the supply, and we end up with 859 milliwatts. If you remember from the P switching for the same example, I think it was 6.1 watts. So the active power consumption is still higher than the static, but static is still pretty significant. I don't know what the heck that is. That might be like 15, 20% of the active, and it really sets a limit to things like sleep modes. Okay, even when if you have your, you know, cell phone completely off, you haven't used it for anything, let's say you even turn off cellular service, you turn off Bluetooth, you turn off Wi-Fi, and you just don't even turn it on, right? You're just sort of sitting in your pocket, displays off, etc. It's still the battery's still draining away. It's not like that phone is going to last for 2 weeks without needing a recharge. Okay, so it's still, even when you're not operating it, this is why it's so bad. This static power is, you'll still need to do a recharge. It just can't just sit there. Okay. All right. What I want to talk about next. I think we talked about this a little bit, about how different threshold voltages. So, every 100 millivolts, you increase your threshold voltage of a device by. This isn't a choice you have. Typically, it's whatever the process gives you these threshold values. And typically, you get two flavors of devices. You get a high threshold device and a low threshold device. And, that sort of affects your leakage currents. Then there's the stack effect. It's something, basically, if you have two devices in series, like a NAND gate, right? So this looks like a NAND gate bottom. But anytime you have two devices in series, the nice thing is this voltage, depending on what it was when the device turned off, isn't always going to be zero. Might have been, if this guy turned off before this guy, or let's say this guy is, it kept the VDD here because this guy hadn't turned on, then this guy sees it doesn't see a gate source voltage of zero. It sees, negative gate sources voltage. So this leakage current ends up being a lot less than the leakage current you'd normally assume from a normal NMOS transistor with a zero gate source voltage. So when you have sort of and that's because it's in series, it reduces the total leakage current, the fact that this guy has lower leakage current. So, and then the more devices you have in series, the more effective this is. And so it turns out that, if you have two devices in series, the total leakage current can be less than you expect, which is a nice thing. Although I'm not sure how you can really use this too well. I think you just have to try to, when things are off, try to turn off devices in a way that, you're doing a sequence where you end up with these intermediate voltages here. But I think in practice it's pretty difficult to do that personally, just given all the other stuff you need to worry about. Okay, guys, and the leakage current, let's see. And lastly, I don't know, this is sort of obvious, but when you have devices that are extremely power sensitive, the best thing you can do is to just totally turn off the supply. When you put something to sleep, just turn off the power supply to the whole circuit. And obviously that's sort of like the nuclear option, to make sure that that's as low as you can go in the power consumption. And the idea is that this is only working if you had special transistors that are particularly high threshold, that won't allow leakage themselves when you're trying to turn off a circuit. Okay, and then the other thing is, you got to make sure when you do that it's not going to screw up, like the block that you're doing that to is not going to be communicating with other blocks. Otherwise, you start giving them intermediate voltage levels that are going to just completely mess up their settings. So I think the note to self is, whenever you do the sort of effective power consumption reduction techniques are also pretty dangerous. And those are clock gating, um, and sort of adjusting the supply or turning off the supply voltages. And you have to be really, really careful with those, because you can, it's really easy to mess up your circuit when you go into these modes. And a lot of times you don't have just two modes of operation. You have 4 or 5. You have sleep mode, you have so-called drowsy mode, you have various types of drowsy modes, and you have different states that you're going from some high power mode into your drowsy mode, or some intermediate power mode to drowsy mode to a sleep mode. And you have to verify all of these modes, that nothing bad happens in all of these mode transitions. Mode transitions is another place where things go really bad. The reason is it just takes a lot of time to verify each one of these mode transitions, and there's just finite time. You'll have the schedule to deal with. You got to tape out your chip, and it's possible that something's gonna fall through the cracks when you're doing that. So again, I think the mode transitions are, you want to do these very, very carefully, and these sort of extreme techniques. So I would call them extreme techniques, but just then when you're doing clock gating and different voltage domains, going across voltage domains. Okay, guys, that's all I was going to talk about in terms of power consumption. Any questions there? If not, I was going to move to the next section, which is something we're sort of going back to analyzing delay, sort of hand analyzing delay. So let's see. Okay. And this is something called, a technique called logical effort. But let's talk about delay. So let's review. This is going back a couple of slides, lectures. And we're talking about delay estimation. Okay, so the most accurate delay estimation, a big part of the design. Okay, one is that your design just actually functions correctly. That means with the right inputs, you get the right outputs. Okay, so that's very important. And then the second thing in terms of functionality is it functions at the speed that's required for your specifications, okay? And so a lot of work's done in analyzing timing when you're simulating your logic designs. And you want to get an accurate analysis of the timing, because it's usually a very, very important specification. And the most accurate thing to do is to simulate it, right? You have your block designed, you've got, hundreds of thousands of gates or whatever you have. And you have these computer-aided design tools that you simulate with. They tell you if you're, at least within the simulation parameters, you're meeting your timing requirements. But the problem is, by then, it's kind of too late if you are having a timing issue, because you've already designed your circuit. So you need to, at the beginning, where you're doing what if analysis, when you're laying down these logic functions, etc., it's handy to have a tool so you can do this what if analysis. You can, at the beginning, decide if your circuit, a particular implementation of a particular block, will meet timing or not at a very rough level. And you can decide if this particular process you're going to be going into is fast enough to meet your specs. You might decide, look, I can't do this in a 180 nanometer and 130 nanometer process. I got to go to a 65 nanometer process. And you also have to be able to make that case to your management and to your customers, because it means that all of a sudden things got a lot more expensive. Okay, so that's where these things we're going to talk about. In fact, everything we talk about is based, talking about hand calculations, and the power. You guys we were doing hand calculations on power. We were doing estimates of activity factor. There's tools that actually simulate it more closely, but the problem is you're simulating something that you already spent the last 6 months, a year designing, and if you got it wrong, it's too late now. So you want to have some hand calculations that are, or Excel sheet calculations that give you an idea of where you're going to be, whether it's speed or power consumption, etc. Okay, so we're back to this sort of hand calculation of delay, and so as a reminder, what we had this really simple model. So let's say if you had something as simple as a minimum size inverter in a process, driving another minimum size inverter. We basically said, okay, the P MOSFETs, we represent those as a series of capacitors and switch and an effective resistance, which in this case ends up being 2R over R, because we made it twice as wide as an N, and R is R as the sort of the effective resistance of NMOS, minimum size NMOS in a particular process. Okay, you make the PMOS twice as wide, and then you get this capacitance. So this is 2C, because the PMOS is twice as wide. So the source capacitance is going to be twice as wide as the NMOS. So C is effective capacitance of gate, source, drain of NMOS. Okay, and PMOS. So this would be again 2C because that's the drain capacitance of the PMOS, and the drain of the PMOS is twice as wide. And then it connects to the NMOS. So I'm drawing this right now. Okay, in fact, this was the P. I'm going to draw the N. That's 1 unit wide, so it only has 1 C. Its resistance is lower, so it's basically 1. How do I keep doing this? It's 2R over 2. This is 1R. And then there is a switch. And then we have the source capacitance and ground. So that's, and then they both have the gate capacitance also. So this is twice as wide, so the gate capacitance 2C. This is 1 times as wide, so it's 1C. Okay, and then, so this whole thing is this first stage. And let's say I want to figure out the delay here. I just need to draw the gate of this guy that I'm driving. So I'm going to add 2C for that gate. So it's this stage is exactly like this stage. So I should have put this down here. So we just have 2C for the gate capacitance of this guy, and 1C for the gate capacitance of that guy. Okay, so this guy here is the delay of my driver itself. So basically, regardless of what I'm driving, of load, this delay always happens. And this guy is the delay caused by the load. Depends on the load. For example, imagine if I was driving, instead of driving one inverter like this guy, instead of driving one inverter, I was driving 10 inverters here. So this would be 10 times as much capacitance. Okay, so this depends on how many things I'm driving, but this doesn't change because it's my own resistances and capacitances. Okay, so if I just look at this guy, I just look at the green part, I can kind of combine these resistances and capacitances. Well, the resistances just end up being R for the PMOS, and then R for the NMOS. And then I'm gonna sum up the capacitances here. I'm sorry, this is both. So it's not just this, but also just driving one other guy like myself. Okay, so a single load. So this ends up being, oops. This ends up being 6C. So 2C for the PMOS drain, 1C for the NMOS drain, 2C for the PMOS gate that I'm driving, and 1C for the NMOS gate I'm driving. So this whole thing is 6C. And then, so if we want to look at the prop delay for rising or falling, let's say falling prop delay, the NMOS is on. So this delay ends up being 6RC. Okay, so 6C times R. Or if you're doing a pull-up, same thing. This guy's off. This is 6RC. Okay, and then this is always the case, regardless of the process. But what happens is, for different processes, we have different R's and C's. So for example, for a 180 nanometer process, this is just reading from chapter 8 in our book. Had some examples of resistance and capacitance for NMOS. So R sub N was 2.7 kilo ohm, and C was 2 femtofarads. This is micron, and micron. And this is a TSMC process in the book, and then there's an IBM 65 nanometer process, and its R sub N was 1.34 kilo ohm, and its C was 0.8 femtofarad. So this guy's RC was, or you can think of it, so RC was 5.4 picoseconds, and this guy's RC was 1 picoseconds. Okay. So basically it says the same configuration in a 180 nanometer process. If I want to know the delay of that, it's 6 times this RC in a 180 nanometer process, or 32 picoseconds. And if I have an inverter driving another inverter in a 65 nanometer process, I have that delay 6 times 1 picoseconds, or 6 picoseconds. So this is what makes this analysis nice, because you're just basically thinking about your logic, what your logic looks like, and you come up with these equations that are dependent. Now, if this was a NAND gate, the driving another NAND gate, it would have a different delay, as we'll see. Delay equation, it would be 6RC, it'd be something a little bit different. And so then you could say, okay, for that case, I have a different equation, delay equation, and I can throw the RC in for different processes and analyze how fast the circuit is, if it's implemented in this process or if it's implemented in that process. So again, a real nice analysis tool for doing sort of what if analysis upfront in your designs. Okay, so it's a nice, nice little model. But so which is nice if you had a single device. But usually you're in a situation where you're looking at, you hardly ever have an inverter, driving a load, and you're just worried about the delay of the one stage. Usually you have like some complicated, I don't know what the heck, some complicated mix of circuits, and it goes on, right? You might have, and this would be like for some data path, right? Let's say you have 20 different gates and you want to see, or it could be 50 or whatever. So you want to see the delay through the whole thing. This is sort of a typical situation you're in. So we have to come up with some methodology to be able to analyze not just delay in a single logic gate, but actually the delay in a multi-stage logic network. Okay, so we're going to look at that, how we do that. And then we want to be able to, see how we can optimize the number of stages, et cetera, in that. So that's what we're going to be talking about in these set of lectures. Okay, so let's do a couple of examples of these delays. Okay, so, and try to give it a shot. I think this is going to be kind of helpful for you guys to look through. And you can look through the book. These are examples from the book. So the first one would be example 4.4. Okay, it says estimate the delay, the prop delay for a unit inverter driving M identical inverters. So basically have one inverter driving not just one, but M inverters. Okay, and as we can just, you guys can take a shot at this and just remember that this guy, let's see if I can do this. This is the model we came up for this guy. Okay, it's a unit inverter model. So we're saying we're going to have this guy, this guy drive M identical guys like itself. So here it was just one. Now we want to do M times more. So let me just, M more than this. So come up with the delay equation. Why don't you guys try to take a crack at this and see what it looks like. Okay. Okay, anybody want to volunteer help me do this? Why don't I pick Logan?
You picked the wrong guy. I'm late.
Oh,
I'm not sure.
oh, no problem. We'll work through it together. So first, let's think about what the load looks like. Okay, so we have this guy as the inverter. Okay, what does the load look like? The load for one guy looks like driving one other guy like itself is 2C and 1C. Okay, what is that? So what do the M of these loads look like? It's just, so it'll just be plain math. So it'll be M times 2C and M times 1C. That's what you're driving. Okay, so if we sum this guy up as being, if you remember, we summed that guy up as, or maybe relate to it as, we sort of summed up all these guys. It just basically was 3C and an R. So depending on whether it's a pull up or a pull down, we had R, and there's like 3C in total, and R for the end. And then we're driving this 2MC and 1MC. Okay. So what we do is we then, pick either a pull up or pull down. Doesn't really matter because we made sure by sizing the PMOS twice as wide as the NMOS, we're kind of like try to make sure the pull up and pull down are the same. So basically you end up having just the inverter itself would have 3RC. So delay would be 3RC for the thing itself. And for all of these guys, you would have 3MRC. So it ends up being, what is it, 3RC 1 plus M. Does that make sense, Logan? Did you manage to follow me?
Yep.
So it's pretty simple. We just have some capacitors, some resistors. Now, like let's say if you're driving a load of 10 other inverters forever and ever, as long as you got a unit inverter driving 10 other unit inverters, you can just use this guy, plug in 10 for M, and end up, so if you had, I don't know, 10 inverters you're driving, M would be 10, and then you would end up with 3RC times 11. So that's what, 33 RC. And now if you were in the easiest one, I guess, is a 65 nanometer process where RC is 1 picosecond. So in that case, the delay would be 33 picoseconds. If I had an inverter driving 10 other inverters. So you can kind of see how we're using this. Another example is if we do example, let's try this one. Example 4.5. So repeat 4.4. So this guy, repeat an inverter driving M other unit inverters. But if, so repeat 4.4, if, oops, if driver is W times wider than unit inverter. Why don't you guys take a crack at that for a few minutes and see if we can take a crack at it. Okay, when I pick on Minas.
Unfortunately, Professor, I might have to let you down there.
No problem. Let's do it together. So think about, so we had this guy. Let's just start with this simplified model. Okay, so this is just all this stuff. We summed it up here. Okay, imagine, so we said like this guy, the resistance is 2R over 2 for the size of 2 wide. And assume it's W times wider. Okay, so what ends up happening is, so when we start with, this guy is 2R over 2. Okay, now imagine it's W times wider. So it ends up being, what happens if you make, what happens to this resistance of this PMOS if you make it wider?
Doesn't your resistance drop?
Resistance drops, exactly. And it's linearly dependent on the increase in width. So basically, if it's W times wider, we just multiply this by 1 over W. So resistance just drops. And then same thing with, if we looked at the NMOS, it's R. And if it's W times wider, it goes 1 over W. So let me put a ground here. So let's just look at this. And then what happens, remember we had the sum of all the drain capacitances of the device itself was 3C. Okay, when we had the unit. What happens to capacitance, the drain capacitance as the device gets wider?
Don't we multiply it by the width because capacitance increases linearly?
Exactly. So we had, so we had 3C, so we multiplied it by 3WC. So that's what a wider driver looks like, a wider inverter by width of W. Okay, now let's look at just this by itself. Okay, if you look at the delay of this by itself without any load, okay, we basically, this part about it is R over W. Let's say I'm just going to look at a pull down times W, 3WC. Okay, the W's cancel each other out, and this ends up being 3RC, which is exactly the delay for the unit inverter. That means because you reduced your resistance, but increased your capacitance by the same ratio, if you're not driving any load, as you make the width of an inverter or any logic gate wider, you're actually not buying yourself anything. Okay, that delay, the self delay, if you want to think about it, stays the same. Okay, so it's not doing you any good with your own delay, but it helps you drive the next stage. Okay, so this was what we had for the delay of itself. Now we're saying we're going to drive, so just like the last one, we're going to drive M unit inverters. Okay, and the load for that stays at this 3MC because those aren't any wider. So I'm going to put in 3MC for all the loads I'm driving. Now for this guy, so this is the self and this is the load. Ends up, we made the width less, sorry, that we made the width longer, so the resistance is lower, times 3MC. Okay, so the nice thing is we made it a lot easier to drive a load. So when you make a driver wider, its own delay doesn't change, but it makes it easier to drive a load. So the total delay is these two together, 3RC plus 3M over WRC, or 3RC 1 plus M over W. And when we compare this, where was it, to this, we see that this delay caused by driving the load gets much less. So as you make this wider, the delay, it makes it linearly easier to drive loads, other circuits. Okay, thanks, Minas. Okay, guys, I'm going to stop here. So with those examples, that was kind of a little bit of a refresher about what we did with the delays. And then on Tuesday, we'll start talking about how we can extend this analysis technique, which is really simple. We're just doing, we've modeled the transistors as these equivalent R's and C's. We're just combining the R's and C's depending on what we're driving. And then we're just getting the RC delay. And we're going to extend that out to a more general approach, which we can handle multi-stage networks. Okay, guys, any questions?
Professor, I think the last lecture video you posted, the video is like private, so we can't watch it.
Okay. Sorry, I must have been pushing the wrong buttons. Thanks for letting me know. I'll fix that.
Yep.
All right, guys. Any other questions?
Sure.
Yeah, good. Was there a question? Okay, guys. If not, have a good weekend. And I'm sorry, I didn't get finished with the grading your midterm. So hopefully I'll be done by sometime this weekend with the midterms. And have a good weekend. I'll talk to you guys on Tuesday. Take care.
Thank you.
Thanks. Bye.
Thank you.